Thank you very much, and thank you for this opportunity to discuss our work in Lyon and for the invitation in this to this great manifestation. So I'm going to discuss a few activities about the metal nanoparticles. So as Pierre said, I'm coming from the Lumière Matière Institute as a neighbor from Lyon. It's a quite large institute with about 300 members. It's an institute that celebrates its 10 years of existence these days. We have a quite large variety of research teams. You can find 6 main groups of teams here. And within this institute, I belong to the femtonano-optics group. You can find the current members of the group. So it's an activity that was started by Fabrice Vallée and Natalia Delfati already 25 years ago. We are currently 7 permanent members and we have 4 PhD students, and we are always happy to welcome new ones. And the name of the group stands for the fact that we are studying nanometric objects, more precisely, mostly metal nanoparticles and hybrid nanoparticles made of a metal component and something else. We are using optics for all this investigation. So we are using, in particular, time-resolved spectroscopy that I will describe in more details a bit later. And we are performing mostly fundamental investigations of the physical properties of these objects. So physical, it means not only optical, but as you will see, we can also address electronic properties, mechanical properties, or thermal properties. And I will give examples of all these investigations. So this is a very brief summary of the lecture, what we will find later. Of course, there will be more details in the following. So I will mostly describe experiments in which nanoparticles, sometimes ensembles, but also sometimes single nanoparticles, are excited by 2 pulsed beams. The first one, the one that comes first, is called the pump. Its role is to excite the nanoparticles, to inject energy. And when energy is given to the nanoparticle, it will heat up. It will become a heater. It will also start to vibrate. So it will be also a mechanical resonator. And to follow temperature evolution, to follow vibrations, that's the role of the probe pulse. So the probe pulse will exploit the fact that the nanoparticles have an optical response which is resonant. They are plasmonic resonators. And this response is affected by heating or by vibrations. So following the change of this optical response after initial excitation will allow to the probe beam will play the role of a thermometer or of a vibration sensor. So that's the key idea of my lecture that I will describe in more detail in the following. So there will be 4 main blocks to this lecture. The 2 first are introductory to present what we are doing in general. And the 2 last ones are more detailed blocks discussing some results about the vibrations of nanoparticles and about their thermal dynamics. So let's start with the first one. It's good to start from a definition of what a nanoparticle is. It will help us to understand what we are doing and what there are fundamental investigations needed to better understand these objects. So I start with one of the many definitions of nanoparticles, which is in nanotechnology, it's a subclassification of ultrafine particle with lengths in 2 or 3 dimensions, greater than 1 nanometer and smaller than about 100 nanometers, and which may or may not exhibit a size-related intensive property. So as you can see, in this definition, there is something very precise and something very vague. What is precise is the range of sizes we are speaking of. It's nanoparticles are objects with dimensions between 1 and 100 nanometers. And what is very vague is this story about size-related properties. So I will explain. So when you have sizes of a few nanometers, it means that the particles will be made of a number of atoms, which is shown here. For instance, for 40 nanometers, it corresponds to a few million of atoms. But if you reduce to 4 nanometers, it's only a few thousands of atoms constituting the nanoparticle. And also, an interesting threshold is 3 nanometers. That's when the number of atoms at the surface of the nanoparticle is approximately equal to the number of atoms in the core of the particle. So with such sizes, a nanoparticle is actually an intermediate system between the atoms and molecules, so few atoms, and bulk solids made of a very large number of atoms. And as such, the physical properties of nanoparticles will, as you reduce size, will evolve from those of bulk solids to those which are almost size independent, to those of atoms and molecules, which are very strongly dependent on size and with possibly quite complex dependence with size. And the difficulty in nanosciences is that this evolution is not general. It's not the same for different properties. It's really something that has to be investigated for each specific property. So to give you a few examples, actually the melting temperature of gold nanoparticles. For large nanoparticles, it's the same as that of gold, so a bit more than 1,000 degrees. For very small nanoparticles, so here, for example, it's 5 nanometers, the melting temperature becomes much lower. It's much easier to melt nanoparticles. Another example here, so it's not on nanoparticles, it's on very thin membranes made of silicon. The thermal conductivity of these membranes is not the bulk one, which is this line here. It's lower and it's decreasing with the thickness of the membrane. So these are two examples of size-dependent properties of nanometric objects. Another example, more from everyday life, or at least from a summer holiday time, is that of sunscreens made of zinc oxide or titanium oxide nanoparticles. These sunscreens have the same ability as more classical sunscreens to absorb ultraviolet radiation. However, they have a different, more transparent appearance. Regarding now nanoparticles, so in nanoscience, actually, before investigating nanoparticles, it's important to have objects to study. And much of the progress in this field has come from improved ability of researchers to synthesize nanoparticles. There are actually many different ways to synthesize nanoparticles. And here you can have a little collection of examples of samples containing nanoparticles. So for instance, here it's an example of a glass doped with silver nanoparticles. Here, these are solutions, so water plus nanoparticles in it, which give a color very different from that of water to the solution. Here, you have nanoparticles which have been produced by electron beam lithography on the surface. So here, these particles are gold nanorings, and they are regularly spaced after the fabrication process. And here, it's still colloidal particles, but it illustrates the fact that chemists are now able to produce quite sophisticated objects. So for instance, here, these are nanoparticles with a metal core and a dielectric shell, silica encapsulating the nanoparticles. And here, it's also a core shell nanoparticle, but with a more complex shape because it is a bipyramid of gold. To investigate these particles, light offers many advantages. So it's a tool that does not require any direct contact with the particles. You can investigate particles without destroying them. Optics is convenient for 3D investigations, and making images is reasonably fast. Light can also be concentrated, both spatially and temporally. So spatially, actually, a beam of light can be concentrated on sizes which are of the order of the wavelengths of light, so a few hundreds of nanometers. And actually, I will show experiments in which there is only one absorbing nanoparticle along such a beam. So this strategy will enable investigations on a single nano-object. I will explain why it is useful to do that. From the temporal point of view, pulse lasers, they deliver very short pulses with durations of the order of 100 femtoseconds, with then a much longer duration between two successive pulses of the order of 10 nanoseconds. So this is a very useful tool to make a sudden excitation of the objects under study. So if we investigate nanoparticles with light, it means that the optical properties of these objects will play a major role in the studies. These optical properties have been actually used rather accidentally since very old times. For instance, this object, which dates from Romanian times, it's an object that contains nanoparticles which are responsible for a very strange effect. The fact that if you look at this object in reflection, it will look green. If you look at it in transmission, it will look red. It's due to the presence of metal nanoparticles in the object, which is exposed at the British Museum. So if you don't want to go to London, you can find easily a video on YouTube to see of how it looks exactly. And metal nanoparticles were also used in the Middle Age to make stained glasses. So these examples are examples of use of nanoparticles without really knowing that they were nanoparticles in the objects. The first to have made more systematic studies of nanoparticles is Faraday. So he managed to synthesize colloidal solutions of gold nanoparticles, and he actually understood that the color of the solutions was due to the presence of small nanoparticles in the solution. And these colors, all these colors, they come from the phenomenon of surface plasmon resonances, which I'm now going to explain. So before that, in optics, we need to be a bit quantitative about how a nanoparticle interacts with light. So here, in this slide, which is a bit technical, I will introduce quantities, which I will use a lot in the following, which are called optical cross-sections. So it's just to define how strongly a nanoparticle absorbs light and scatters light. So it's defined for illumination of the objects by a plane wave, which is characterized by its intensity, so watt per meter square. The nanoparticle absorbs part of the light, which is converted into heat. It scatters part of the light, so redirect part of the light. So the associated powers are in watt. And as a result, the incoming beam is attenuated. Its power is reduced by the effect of absorption and scattering. And the sum of the two is called extinction. So cross-sections are just the ratio between absorption, scattering, or extinction, which is the sum, powers, divided by the intensity of the laser beam. So they are surfaces, and they are independent of incident intensity, at least in the linear regime, and they quantify how strongly a nanoparticle interacts with light. So then this cross-sections, they are quite difficult to estimate for complex nanoparticles, but they can be directly computed, analytically computed in a few simple cases. And one of the simple cases is that of a small nanosphere, so small in the sense that its radius or diameter is much smaller than the wavelength of light, standing in an homogeneous medium. So the same medium all around the sphere. So in this case, there is an analytical exception to for the extinction cross-section. So how much the particle absorbs and scatters light. So you see there are a few parameters in this expression. There is the volume of the particle, the wavelength of the light here, and dielectric function, so which are just the square of the refractive index with which you may be more familiar, of the particle itself. So it's a complex quantity because the particle is generally absorbing, and the environment. So it's a real quantity if the environment is transparent here. So a first key message is that the optical properties of a nanoparticle depend on the composition of the particle itself, but also on the environment in which it is, of the environment around it. A second key message, so here one has to look at this denominator. So usually in the denominator, the dominant term is this one, but the first one. But actually, this first term for metal nanoparticles, it's something that can be zero. So if you have a small denominator, it means that the extinction of the particle will be much larger. The particle will very strongly absorb and scatter light. So it's called the surface placement resonance of of metal nanoparticles. Sorry, I pressed the wrong button. Okay, so and this condition for resonance, so you see it has one, the real part of the dielectric function of the particle itself, so something related to the composition of the particle, and here something related to the composition of the environment. So again, it depends on both compositions, and in particular, it will not be the same depending on whether you have, for instance, a silver nanoparticle or a gold nanoparticle. The resonance condition will occur at different wavelengths. So more precisely, you have here some examples of the extinction spectra of silver and gold nanospheres in water. For silver nanospheres, you have a very sharp, narrow, and symmetric resonance here, which occurs at the border of the ultraviolet and visible range near 400 nanometer. And for gold, you also have a resonance, but it's not at the same wavelength. It's near 550 nanometer. And also the resonance looks quite different because it's much broader and it's not symmetric because it overlaps with the background of bulk gold absorption. Okay, and so all this was for spherical nanoparticles. So in this case, and small nanoparticles. In this case, the resonance condition is only set by the composition of the particle and of the environment. However, things are different for a nanoparticle with more complex shapes. For instance, for gold, for elongated nanoparticles, such as nanoellipsoids, the extension cross-section becomes a bit more complicated with the appearance of shape-dependent factors, which also affect the resonance condition. So the result of this is that the resonance wavelengths and thus the color of solutions of elongated nanoparticles depend on how strongly elongated they are, depend on the ratio between their long and short axis. So you have a concrete example of this here with solutions of gold nanorods. You can see electron microscopy images of the objects here. They are more and more elongated along this direction. And as you see clearly, their color changes. And here is the corresponding resonance wavelengths. For not too elongated particles, is still in the visible range here. But as the particle is more and more elongated, the resonance belongs to the infrared domain. So this shows that the plasmonic resonances of metal nanoparticles are quite tunable by playing with the shape of the particles, and it's very useful, for instance, for biological applications, which would require infrared resonances. These resonances cannot be achieved, not easily be achieved with the spheres, but they can be easily achieved with elongated objects, such as these ones. Okay, so that was for the first part of the talk, devoted to the objects that we study, metal nanoparticles. So now let's address the tools that we use to investigate them. So the main tool is time-resolved spectroscopy. So the principle is very simple. It is to illuminate a sample containing nanoparticles with pump and probe beams are made of pulses with a duration of a few femtoseconds. So as I said earlier, the pump excites the sample, and the probe will read the induced modification of the sample optical response. So if you want an analogy, the pump launches the dynamic, so it's like giving a start, and the probe monitors the state of the system at various delays, various subsequent delays, as in a chronophotography experiment, which is shown here. So what we are doing in more detail, what we are doing, it's not really taking a picture, it's measuring one optical quantity here, which will be the relative change of the transmission of the sample. So it's more a number characterizing the system measured as a function of the delay between the pump and the probe. So from a practical point of view, this is what such an experimental setup looks like. So it starts with a laser source delivering pulses. We need different colors for the pump and probe. So this can be achieved, for instance, by nonlinear optics, by separating the light produced by the source in two arms, and having a nonlinear crystal on one of the paths. This will create photons with twice the frequency of the starting one. Then one needs a device to control the time delay between the pump and the probe beams. So it's typically done using a mechanical stage that will shorten or lengthen the path of one of the beams. So as a result, it will arrive before or after on the sample, which is here. And also, a technical but important part is that in these experiments, one wants to measure very small signals, relative transmission of relative changes of transmission that can be as small as 10 power minus 7. So very little, very small modification. So this requires a very sensitive setup. So this is achieved by a modulation strategy. So the pump intensity is modulated, and also lock-in detection is used. And also the detection can be differential by subtracting a reference intensity coming from the laser. That's to get rid additionally from the intensity of the intensity fluctuations of the laser sources. So here is an example of the signals that we can obtain for metal nanoparticles. So this one was actually acquired for very small nanoparticles made of platinum. So very small, it was 1.5 nanometer diameter. We show it because it's very nice. It's a nice example of the measurement. So it's a time result signal, so that as I've just described. So here you can see relative transmission changes. Here you can see the delay between the pump and probe beams. So at delays before 0, the system is probed before its excitation, so there is no signal. However, when probing is achieved after the excitation, you can see three structures on the signals. So 1, 2, 3. So 1, it's a peak of large amplitude. This corresponds to the effect of exciting the objects, injecting energy in them, and also to the effect of internal thermalization, because the energy is injected in the electrons, and first redistribution with the ionic lattice of the particle will take place. So these are internal energy exchanges. So then here you can see oscillations in the signal. These oscillations here, they are the signature of the vibrational motion of the particle. The particle vibrates and its optical response is periodically evolving during these vibrations, and this leads to oscillations in the time-resolved signals. And then number 3 here, it corresponds to cooling of the nanoparticles. It means that you have injected energy in them. This energy will leave the particle, will be dissipated towards the environment of the particle. So it's cooling of the particles. Okay, so everything I presented up to now, that was experiments on a large number of nanoparticles at the same time, which was the configuration with which this type of experiment started. However, there can be a problem associated with this approach. Is the fact that the signal corresponds to measurement over different nano objects, which are never exactly the same. So, for instance, which have slightly different optical responses, which vibrate at slightly different frequencies, and which cool at with slightly different time scales. So there is always an averaging process involved with such experiments. In some cases, it's not such a problem, but in other cases, it can be a big problem, especially when one is interested in damping phenomena, for instance, vibrational damping. You can see here that when you perform experiments on assemblies and on a single particle, you will have here a very strongly damped signal, here a much less damped signal. The reason is that in the ensemble measurements on a large number of nanoparticles at the same time, the particle vibrate at different frequencies, and so they dephase progressively as a function of time, and this is responsible for additional damping as correspond as in the single particle case. So the key message here is that we can obtain more quantitative information about physical phenomena when if one is able to measure single particles, individual particles. So how to do that? So single particle or single molecule detection, it's a field that was born in 1989 with this paper by Morner, with here, who reported the first optical detection of a single molecule in a solid. And then the field evolved very quickly, and in 2014, Morner, together with two other researchers, was awarded the Nobel Prize of Chemistry because detecting single particle or single molecules, and in particular in the field of fluorescent microscopy, has led to considerable improvement of imaging in biosciences. So their Nobel Prize was related to fluorescence-based methods in which the single objects are optically excited and they emit fluorescence light that has a different wavelength from the absorbed light, and therefore that can be separated from the incident light using a series of filters and a dichroic mirror. For metal nanoparticles, they are weakly fluorescent, so it's not something we can use. So we need other tools exploiting other phenomena than fluorescence to detect single gold particles. So several tools have been developed. For instance, dark field microscopy. It's a tool that selectively detects the scattering by single nano-objects. So it's a simple tool, but hard to use for quantitative studies. Also, photothermal techniques use the absorption of by single nano-objects. So the idea is that once a nano-object has absorbed light, its refractive index and that of its close environment will not be the same as previously, and this will change the path of a second beam. So it's a very sensitive method, however, more complicated than the first one because it requires two different light beams. And then the technique that we use in the laboratory is called spatial modulation spectroscopy. So this one uses scattering, this one uses absorption, and this one uses extinction. So it's sensitive to both absorption and scattering. And as you will see, it's a very quantitative and highly sensitive method that I will now describe in more detail. So the idea behind this method is quite simple. It is to illuminate a sample with a very strongly focused laser beam and to detect the attenuation of the beam when a nanoparticle is present in the beam. Because when there is a nanoparticle, it will absorb and scatter light, so less light will be transmitted through the sample. So one wants to detect this attenuation. The problem is that this attenuation can be quite small because the light beam is concentrated on a few hundreds of nanometers. And if the particle is much smaller, it will, the attenuation will be a tiny fraction of the incident beam, relative attenuation of much, much less than 1. So to detect this small attenuation that can be even smaller than the intensity fluctuations of the light beam, one needs a sensitive approach. And the main idea is to make the attenuation oscillating in time and to detect it with a lock-in detection. So for this, one has to modulate something in the system to allow this detection approach. What Morner did in his first paper was to modulate light frequency. What we do in the lab is to modulate the sample position under the beam. So we move periodically the sample so that, so it's shown here. So our setup, we have one objective to strongly focus light, one objective to recollect the transmitted light. In between, we have the sample, which is typically made of nanoparticles deposited on a solid surface. And this sample is mounted on a vibrating stage, so it's moving like this periodically as a function of time. And when we do so, when there is a nano object in the focused beam, the position of the nano object is not constant anymore. So when it is close to the center of the beam, it will more strongly absorb and scatter light. When it is close to the border, it will less strongly absorb and scatter light. And as a result, the transmission signal that we measure is not constant anymore. It contains components at once and twice the modulation frequency that can be efficiently detected. And additionally, these components are proportional to the extinction cross-section of the particles through parameters which are related to the amplitude of the modulation process that we can know, and to the distribution of the light, of the intensity of light in the focus beam that we can also know. So from the signal that we measure, we can directly extract the extinction cross-section of the single nanoparticle that we investigate. So it means that with this tool, we can perform two things. We can perform macroscopy, that is, we can make images of the surfaces of our samples. So in these images, due to the modulation process, each nanoparticle has a quite specific image. It looks like this: a series of three peaks, an intense one in the middle, and two side peaks at the top and bottom parts. So that's the image of one nanoparticle. And so it means we can detect nanoparticles even if they were purely randomly deposited on the surface. And then we can also perform spectroscopy, that is focused on one nanoparticle and measure its extinction spectrum as a function of wavelengths. And so here that's the spectrum of metal nanoparticle, which shows, so it's a gold nanorod. It shows resonance near 800 nanometer wavelengths. And we can also measure this as a function of polarization. So here, also for a gold nanorod, since the object is very elongated, its response is not the same for all polarizations. It's maximal when the polarization is aligned with the rod axis, and it's minimal when the polarization is transverse to the rod direction. So with this tool, we can, for instance, determine optically the orientation of a single nano object, even if we do not, if the optical resolution does not allow us to really see the shape of the object on the image. So So measuring quantitatively the optical response is actually very useful for us because it means that even if, as I just said, the optical resolution is not does not allow us to see directly the shape of the objects, we can actually deduce information about the shape and size of the objects that we study just from their extinction spectra that we measure. So here you have a few examples for simple objects. So on the left, nanospheres. So a nanosphere will produce more absorption and scattering if it is bigger. Remember, in the formula I showed, the response was proportional to the volume of the object. It means that from the quantitative measurement of the amplitude of this spectra, we can deduce what is the size of the particles that we investigate by comparison with models. We can also do the same for more complex objects, for instance, elongated nano-objects such as gold nanorods. So from the polarization-dependent response, by comparison with simulations, we can extract the size of the object, the shapes, that is both the diameter and the length of these objects, and also, as I just described, their orientation, how oriented they are on the surface. So this is for simple objects. It's not always possible to do some such a precise optical characterizations. For instance, if we have too many unknown parameters. So in some other cases, when we really want to know the morphology of our objects to use it later in the modeling, what we do is that we combine optical experiments that I've just described with an imaging technique with very high resolution, such as electron microscopy. So to do so, so technically, it means that to do so, we have to use substrates which are both, which can be used for both optics and electron microscopy. So we typically use very thin silica membranes, and we also need some marks on our sample to be able to find the same region for optical characterizations and for electron microscopy characterizations. And at this using this approach, it means that after optical measurements, we can, if needed, make an image, an electron microscopy image of the nanoparticles that we have been investigating. Okay, so regarding time-resolved experiments, so here I've already discussed this type of experiment in general. When they are applied for on single nanoparticles, what has to be done is to overlap a very focused point beam with a very focused probe beam, and to overlap them on the single nanoparticle. So these are not easy experiments because one needs to preserve this alignment as a function of time. In this single particle experiments, I should also say that the signal that we measure is actually directly proportional to the transient change of the optical of the extinction cross-section of the object as a function of time, which results from changes of dielectric function and morphology. Okay, and finally, I want to stress also that apart from this optical characterizations, another tool that is very precious for us, and which is what mainly what I'm doing in the group, it is to use numerical simulations to characterize the optical properties of our nano objects. So as you have seen, we are using optical techniques which strongly exploit the optical response of metal nano-objects. So we perform a lot of optical simulations in which we compute the optical response of nano-objects in their actual environment of experiments, so including the fact that they are usually deposited on a solid substrate. So we can extract absorption and scattering spectra by numerically solving Maxwell equations. We also perform acoustic simulations, so that's for the vibrational part of our studies. So with these simulations, we can see what the vibrational modes of an object look like, and we can also access to their frequencies and quality factors. I will show examples of it in the next part. So this is done by numerical resolution of another equation, which is Navier equation. And we also use similar tools for modeling the thermal dynamics of nanoparticles. So here we numerically solve a Fourier equation, and so we can, starting from an initially heated nanoparticle and an initially non-heated environment, we can see at subsequent instance what is the temperature field in the particle and in the environment. So it's typically something we do after the experiments to better understand what we have measured. In some occasions, we have also performed simulations first, and they give us ideas of interesting phenomena, which led to ideas for experiments, as in these two papers. Okay, so what are our motivations for studying energy transfer at the nanoscale, on which I will concentrate in the two next parts of the talk. So the key idea here is that at the nanoscale, there are strong differences between the modalities of energy transfer with macroscopic scales. So three of them are listed here. The first main difference is that the characteristic times, or at least some of them associated to energy transfer processes, are much faster. The characteristic time, in some cases, scale as a size. So as you reduce size, you go to shorter and shorter characteristic times. Also, what is specific to the nanoscale is that interfaces play a much greater role. It's particularly the case in the context of heat transfer at the nanoscale, because in heat transfer, as soon as you have an interface between two different media, you will have a discontinuity of temperature, which is characterized by so-called Kapitza resistances. So the idea is that an interface produces a thermal resistance opposing heat transfer. And these interfaces cannot be at all neglected when studying, for instance, the cooling dynamics of very small objects. Another specificity of nanoscale heat transfer is that when you work on very small objects, in some cases, the size of the object can become smaller than characteristic lengths of the material. So, for instance, phonon mean free path, the typical length that a phonon can, on which a phonon can propagate before encountering a collision. So when this happens, it means that the thermal transport cannot be assumed anymore to be something diffusive with many collisions. We enter another regime, which is called the ballistic regime, in which there are much less collisions. So all this constitutes fundamental motivations for fundamental investigations of heat transfer phenomena at the nanoscale. There are also some applications associated to this work. It's not what we primarily work for in the group, but it's something that can be a later outcome of the research. So, for instance, when you investigate the vibrations of very small objects, these small objects can be used as nanobalances the idea is that the vibrational frequencies of the object will be modified when mass is deposited at on its surfaces. Also, metal nanoparticles, they constitute generators of very high frequency acoustic waves and of heat. So in the later context, the use of nanoparticles as heat generators is used, for instance, for photothermal therapy. The idea being that to bring nanoparticles close to a tumor, and then to illuminate the particles so that they will absorb light, they will heat up, and the temperature will locally increase and possibly destroy the cells. Okay, so I'm coming now to the part devoted to the vibrations of nano-objects. So just as a start, to realize that we are dealing with very high vibrational frequencies. Here you have an estimation of the frequencies of vibrational modes. So it's done just by saying that phonons in infinite materials have a frequency which is the sound velocity divided by the wavelengths. And if you have localized modes in nanoparticles, you have a cavity effect, and the wavelengths can be only approximately the size of the particle or the size divided by an integer. So it means that the vibrational frequencies are at least of the order of sound velocity divided by diameter. And when you put the numbers for particles of the order of 10 nanometer, the frequency will be of 100 or gigahertz to about 1 terahertz. Of course, it's just to realize the range of frequencies we are dealing with. This can be made much more precise for a given object by numerical calculations of the vibrational modes. So before discussing the time result signals obtained on metal nanoparticles, I just want to quote two related studies that started this field of research. So the first one is with time result spectroscopy, but not on metal nanoparticles, but on thin films. It showed that the vibrations of thin films can be used as a generator of vibrations in the supporting substrate. And the second one was made on nanoparticles, but with another optical technique as time result spectroscopy, which is Raman scattering. It was the first detection of the vibrational modes of small nanoparticles. So both studies were done in 1986. Right. So now let's discuss the signals that we have first measured at the end of the 90s on metal nanoparticles. So here, as I said before, the vibration, the signature of vibrations are these oscillations of the signal. Here, you have signals measured with large nanoparticle, 26 nanometer diameter, and a much smaller one, 6 nanometer diameter. You can see actually that the period of the oscillation is very different. And actually, this period is actually exactly proportional to the diameter of the nanoparticles. It was seen for nanoparticles embedded in glass, and the very same trend was observed for nanoparticles dispersed in liquids. So to understand where it comes from, so one has the choice between two main approaches for discussing vibrations: atomistic models in which all the atoms forming a nanoparticle are taken into account, and their motion is solved for interaction described by potentials. And one can also use continuum models in which the atomistic nature of the nanoparticle is not taken into account. They are described as a continuum medium. And what is solved is this Navier equation, which relates the temporal and spatial derivatives of displacement. That is how locally, what is the deformation as compared to the equilibrium position. So this, so I will summarize to make it short. Actually, for spheres, the theory of the vibrational modes of spheres was done by Horace Lamb at the end of the 19th century. Not for nanoparticles, just for vibrations of spheres in general. And he found that modes can be classified in many different categories, so it looks a bit complex. However, for time-resolved experiments on nanoparticles, the vast majority of these modes cannot be excited. Actually, only simple modes called radial modes, which have an isotropic displacement, can be excited. So it's only a tiny category. And among these ones, actually, the fundamental one, which is called the bracing mode, which does not have a displacement node, this one is excited more efficiently. So it's actually this mode that is only this mode that is detected in time-resolved experiments on nanospheres. And actually, the vibrational periods that were measured are in very good agreement with that computed using Lamb theory for this mode. So for just to mention that if the objects are more complicated, so for instance, for an elongated object, here it's not only a single mode that is detected. For instance, for gold nanorods, we have two modes with very different features which are detected. One with a small period associated to transverse vibrations with a period proportional to the diameter, and one with a much longer period proportional to the length, which corresponds to longitudinal vibrations. So let's go back to spheres. So with spheres, as I said, we detect one vibrational mode, which is proportional, whose period is proportional to diameter. And in the previous experiments, we had this proportionality between the period and the diameter. So it was observed near 6 nanometer diameter. And of course, a goal at this time was to look at what happens here, smaller nanoparticles, with the question, can one still describe the vibrations of very small nanoparticles of only 1 or 2 nanometer large diameter with a continuum model? So I will briefly present 2 attempts to verify how elasticity works at the for small nanoparticles. So the first attempt was done about a bit more than 10 years ago. What was needed was to have very small nanoparticles with a size not too different from one nanoparticle to another. So it was done by our colleagues in Lyon by using a laser ablation protocol combined with a selection by size of the produced nanoparticles, because this laser ablation produced nanoparticles with a large variety of diameters, but a sub-category with a specific kinetic energy of these particles can be selected, leading to samples with either deposited or embedded nanoparticles with a few nanometer size. So we perform experiments on these particles here. The vibrational frequencies become really very, very high, more than 2 terahertz for the smallest particles. However, apart from this these high frequencies, we are still in the line of proportionality between period and diameter. And this was confirmed by simulations, numerical simulations performed by Mexican colleagues. Whatever the precise shape of nanoparticles that they consider, they still approximately recover this proportionality between period and diameter. So it means that it's a very surprising result, but still supported by both experiments and simulations, that even if you have a nanoparticle with less than 100 atoms, it's still described by using continuum elasticity, completely neglecting the atomistic character and using the elastic constants of bulk metals. So the second attempt in this domain, more recent, was done this time with chemically produced nanoparticles made by our colleagues from Lyon. So the chemists are able to do very nice objects. They can do gold nanoparticles with a precise number of gold atoms. It can be 25, it can be 38, it can be 68. This number is perfectly known. However, the complication coming with this synthesis is that it's not pure metal, pure gold nanoparticles. There are ligands around them, and actually the size of the ligands is close to the size of the gold core. So one has to remember in the modeling not to forget the presence of these ligands. So here two time resolved experiments could be done. So in this case, it was not one mode that was detected, but two ones with very different frequencies and periods. The reason for this is that such small objects, they cannot be perfectly spherical. They have some deviation from sphericity, which is sufficient to allow the detection of other modes that are not detectable for perfect spheres. Focusing on the bracing mode, the same as before. For the largest particles, it's still along the same line as before. But for all small nanoparticles, here this time there is some deviation. So the question is, do these deviations arise from a breakdown, a collapse of the laws of elasticity at the nanoscale, or do they arise just because of the presence of ligands around the particles, which cannot be avoided with this synthesis? So this was answered using numerical simulations by our Mexican colleagues. So when they do simulations in the same conditions as experiments with the same objects, they find frequencies which have the same trends, which do not show a linear evolution with diameter. So it's in good agreement with simulations, with experiments. And what they can do in simulations, something that is not possible in experiments, they can remove the ligands around the particles, make calculations for pure gold clusters. And when they do this, they recover the perfect, quasi-perfect dependence between periods and diameters. So it means that what we saw, these deviations here, they were not due to the fact that elasticity of small gold clusters is very different from larger objects. They just come from the fact that the experimental objects were surrounded by ligands. So in that sense, the conclusion of this part is that the elasticity is a property that is very robust towards size reduction. Elasticity of small nanoparticles is still, at least in this experiment and for these vibrational modes, is still the same as that of a much larger object. So now I want to address a second topic about vibrations of objects, which is that of vibrational damping, which I have just introduced previously to motivate single particle experiments. So when you perform such single particle experiments, the damping of the oscillating signal that you see here actually reflects the actual damping of the vibrational modes, and it arises because of two different processes. First, intrinsic mechanisms occurring within the particles, which are not very well known at the moment. And second, another process, which is the fact that the vibrations of a nanoparticle do not remain forever localized in the particle. They will propagate towards the environment, and therefore acoustic waves will be emitted in the environment, which will reduce the vibrations of the object itself. So several experimental configurations have been used to study this damping phenomena. Supported nano-objects, which is the configuration that I will focus on, but also optically trapped nano-objects in liquid and suspended nano-objects. So this configuration is interesting because it avoids, it produces higher quality factors when the suspended part is in air. However, it's limited to nano-objects with at least one large dimension, so either nanowires or nanoplates. So let's start with previous investigations of single supported nano-objects. So here you have a few summaries of a few previous experiments. Damping time as a function of period. So a straight line like this corresponds to a constant quality factor. So you can see several things on these different plots. So usually the quality factors are not very high, a few tenths typically. Also, typically the data is elongated vertically. It means that even if you work with different nano-objects which have approximately the same size and therefore the same frequency, they will have very large differences in quality factors, which was initially ascribed to the fact that when a nanoparticle is deposited on a solid surface, the quality of the contact between the particle and the surface may be different from one nanoparticle to another. Recently, we wanted to see whether these vibrational quality factors, do they actually depend on the morphology of the particle. So to do this, you need to synthesize nanoparticles with not exactly the same shape. So we did that by considering gold nanodiscs produced by electron beam lithography on a solid substrate. So a nanodisc, it's an object that is characterized by two dimensions, diameter and thickness. And with electron beam lithography, it's possible to produce multiple nanodiscs with the same thickness, but with many different diameters, and therefore many different ratios between diameter and thickness, which will be the parameter of interest in the following. So with our tools that I've described previously, we detected single nanodiscs. We selected the most circular ones using the fact that very circular nanodiscs have an optical response that is independent of polarization. Then we measured the vibrational response. So here you have each signal corresponds to a measurement on an individual nanodisc with, however, different diameter over thickness ratios. Here, 3.5, one vibrational mode detected, 3, beating pattern due to the fact that we have two close vibrational modes which are detected, 2, which corresponds to two vibrational modes which are quite far in frequency. And the most interesting situation is here. You can see we detect one vibrational mode, but we see much more oscillations than in other cases before damping is complete. So it's something. It's something that we investigate complementarily with numerical simulations, in which we include the gold nanodisk and the substrate on which it is supported. Our simulation allows to simulate the vibrational spectra of the object. So you see multiple peaks, which each correspond to vibrational modes, from which we can estimate frequency and quality factors. We compare with simulations, we see a very good agreement in terms of the detected frequencies. And the most interesting feature is here. So we compare here quality factors in experiments and in simulation. So what you see is that usually the quality factors are low, of the order of 20 here, also of the order of 20 here. But for specific aspect ratios, near 2 or 2.5, we have in both experiments and simulations a strong enhancement of vibrational quality factors. So it means that we are in situations in which for specific shapes of the nanodisk, we prevent emission of acoustic waves in the substrate. We block this emission, and the damping, the vibrational damping of these objects just come from internal effects. So this was one of the key results obtained by Fabio Meneghini, who did his PhD in the group and who defended in 2018. Right. So actually, so the experiments and simulations were done a long time ago, but even after this project was finished, we could still not really understand what exactly was happening, what was the phenomenon at the origin of this increased quality factors. And it's something we could do much more recently. So we were very happy to understand the origin of this phenomenon. It's actually a particular manifestation of what is called weakly damped Friedrich-Wingen modes. So I will not describe this in details, just tell you that there are two ingredients for creating such modes. You need to start with two resonances of close frequencies. So this can be two modes of the nanodisk which vary, whose frequencies vary differently with the geometry that can become of close frequency accidentally. And then you need that these modes are damped by emission of waves in the same medium. It's the case in our experiments because emission occurs for all modes in the supporting substrate. And in this case, these waves can interfere. When interferences are constructive, it means that the wave is reinforced. We have more acoustic radiation, and therefore we have a more increasingly damped mode. But interferences can also be destructive, in which case the strength of the amplitude of the emitted wave in the substrate is reduced, meaning that the vibrations remain more localized in the object. So it's what happens in our experiments, and it's also not a very general phenomenon that is not restricted to the acoustics field. You have similar manifestations of this phenomenon in optics, which were described first in this paper in 2017 that show that this effect can be used to make dielectric resonators with very high quality factors. Okay, so that's the end of the acoustics part. So as you see, elasticity is very robust in the for very small nanoparticles. They still can be described using a model that was developed for describing the vibrations of planets, for instance. And regarding energy transfer to the environment, in the last years, we have better understood the vibrational coupling between a nanoparticle and its substrate, and we have partly managed to increase the associated quality factors. So I will now discuss a bit nanothermics. So I don't know how much time I have left. Okay, it will be okay. So I think it will be about 15 minutes, and then it will leave some time for discussion. So why is the thermal cooling of nano objects? What is it? Why is it of importance? So I think there are many people in the room working in computer science, so they might be interested by this. The size of individual components in processors have become smaller and smaller, and now the dimensions of transistors can be below 10 nanometer. And in computers, what has become critical with some such small components is to cool them efficiently, because one generates large power, and if this power is not dissipated correctly, the components will become warmer and maybe damaged. So it's a field where one needs good understanding of how very small objects cool down, and one aims at making this cooling much as fast as possible. In other fields, for instance, thermoelectricity, which tries to convert heat into partly heat into electricity. On the contrary, here one needs media with low heat conductivity and high electric conductivity, which is not so easy to make. And atoms are made to do this by nanostructuring matter. So this is for a brief discussion of the technological importance of this field. As I said, from a fundamental point of view, at the nanoscale, interfaces are really playing an important role. That has to be clarified. So what can we learn in this field with our time-resolved experiments? We can learn two things. First, we can measure how fast a nanoparticle cools down after its excitation. So to cool down, actually, it requires two different processes. First, the energy that is in the particle, it has to cross the interface. And we have seen that it is limited by Kapitza resistances. So it will not be infinitely fast. And then, once energy is in the environment, it has to spread far away from the nanoparticle. So this is also not instantaneous. So in general, in cooling experiments, we will be sensitive to these two phenomena, meaning that we can learn things about the interface. We can, for instance, estimate, access the thermal resistances of interfaces. And we can also clarify the modalities of heat propagation close to the, in the environment, close to the nanoparticle. And here, so we can estimate the conductivity, but we can also see whether there is a signature of non-diffusive effects. It's something that we didn't see yet in our experiment in Lyon, but which was seen by American researchers in the systems in which they performed time-resolved experiments on arrays of nanolines. And what they found was that for very small nanolines, they could not use the same model as for very much larger nanolines. And the interpretation was that the nanolines are too small for thermal transport below the nanolines to be assumed to be diffusive. It has become quasi-ballistic. Also, we are working with light. So we probe the thermal dynamics through the change of optical response that it induces. So here, it's there is a complication of the study, in the sense that we have seen previously in the first part of the talk that the optical response of a nanoparticle depends on both the properties of the particle itself and also of its environment. So when a nanoparticle is heated, it will cool down. The surroundings will also become warmer. And actually, the two dynamics, the heating and cooling of the environment and the heating and cooling of the surroundings, will both contribute to the signal that we measure. And it means that we have to separate the two contributions, but the good thing is that we will gain information not only on the particle temperature, but also on the evolution of temperature in its environment. So I will discuss a few projects in this field. So the first one we did in 2009 was to consider metal nanoparticles in glass, so embedded in the glass. We found that in this situation, the interface and environment contributions are of the same order. It's very important to include these two processes in the description of the thermal dynamics to reproduce the experimentally measured one. And we also varied the composition of the nanoparticle and of the glass to see how the thermal resistance depends on this on the two compositions. And we found that actually the thermal resistance correlates with is the acoustic mismatch at the interface, which controls the efficiency with which phonons are transmitted and reflected at the interface. Another more recent study was for gold nanoparticles in ethanol. So here, ethanol is a medium that has a refractive index, which is very, very dependent on temperature. So when the energy of the nanoparticle is communicated to the ethanol, it will heat up and it will affect the time result signals. So we could, modifying the probe wavelength, allow us to tune the relative contribution of nanoparticle heating and environment heating. So we could actually estimate the contribution of the two to our signals, and we also could achieve a very funny situations in which a specific probe wavelength, in which actually the signals that we measure do not reflect anymore nanoparticle heating. They purely reflect the ethanol heating, and then on a much longer time scale, cooling. So we have this time a thermometer, not of the particle, of the temperature of the particle itself, but a thermometer of the temperature of the closed environment of the particle. Another system that we investigated is the same as that I discussed for the vibrational studies. It's gold nanodisk on sapphire. So here, actually, changing the wavelengths changes a lot the amplitude of the signals, but not their shape. This actually means that we are never sensitive to heating of the sapphire. Here we are only sensitive to heating of the gold nanodisk with, and this heating translates with a very different efficiency into an optical signal. In this situation, we have our signals are just proportional to the evolution of the nanodisk temperature. So it's quite almost perfectly exponential decay times a coefficient which represents the sensitivity of the optical response of the nanodisk to its heating. So I will briefly, as time goes, I will very briefly discuss the two aspects. So regarding the sensitivity to the sensitivity to heating, it's something that we can model. So to do that, we need to know how the dielectric function of gold depends on temperature. It's something that was known from previous experiments and previous models. And we need also to know how the optical response is affected by a change of refractive index, something that we can know from optical calculations. So once we have this, we can we have simulated sensitivity to heating, which depends on wavelengths. As you can see, this sensitivity can be its absolute value is very large here as compared to other wavelengths. It's very close to the surface placement resonance position. So it means that if we really want to detect, to be sensitive to the heating of a nanoparticle, we have to work here. But it can also be zero here or here. It means that here our signals are not sensitive anymore to the heating of the nanoparticles. And regarding how fast the nanodisk cool down, so we investigated how this depends on geometry of the nanodisk. So it depends very little on the diameter of the disk. You can see diameter here and here have almost no effect, but it depends very strongly on the thickness of the disk. This and also the dynamics are almost perfectly exponential in all cases. It's actually the signature of a process that is cooling that is limited by propagation of heat at the interface. The interface is the limiting process to allow cooling of the disk. So meaning that by comparison with simulations, we could extract the thermal resistance of the samples of each measured nanodisk. So it was seen to be very close from one nanodisk to another in the same sample. And we had a slight difference. It was slightly higher for the second sample, because the contact between the objects and their substrate was slightly different for the two samples that we used. And this was one of the results of the PhD thesis of Romain Rouxel, who defended 2 years ago. Okay, so just before finishing, this is just to give you a flavor of what a very recent experiment. So we are now performing with disks produced by chemistry. The good thing of such a chemistry production is that we can deposit the disk on the substrates that we want. And in particular, we could deposit the disk on very thin membranes. And here, what we found was that the cooling becomes much slower when the disks stand on a thin membrane. It's because the silica that we used does not conduct heat as efficiently as sapphire, but it's also because heat spreading is limited on thin membrane, because it will mostly be diffusion in 2 dimensions instead of 3 dimensions, so it's less efficient. So the disk takes longer to cool down. Okay, so I've reached the last slide of my presentation. So regarding the tool that I've described, you've seen that combining optical time-resolved investigations on single particles plus numerical modeling, this allows very quantitative investigations of the physical properties of particle, especially here I showed vibrational properties and thermal properties. We can deduce from these experiments the dynamics of vibrations and of heat transfer. And we can also, playing with wavelengths, we can study the sensitivity of our optical signals to these dynamics. And with this, we can decide to, we can use this as a tool to study a dynamics that we are interested in, or to avoid it in the signal if we are not interested in it. Okay, and with this, I would just finish by thanking all my colleagues of the Femtonan Optics group in Lyon, all the collaborators with whom we work, because such research projects require multiple interactions. And thank you for your attention.